For the past few years, the whole story of AI has felt like this massive race to the top, right? Bigger models, more data, more power. But what if that entire race is, well, based on a flawed map? What if we're not just dealing with scaling problems, but a full-blown crisis of reality? Okay, let's get into it. Because a new way of thinking about AI architecture suggests we might be on the edge of a huge, huge shift. So this is the core idea, and it's a really powerful one. The argument is that we're basically in a Ptolemaic crisis. Now think about that for a second. For over 1,400 years, Ptolemy's model of the universe, the one with the Earth smack dab in the middle, was the state of the art. And here's the crazy part. It kind of worked. I mean, you could use it to predict where the planets would be, well enough to navigate. But the whole thing was built on a fundamentally wrong idea. So to make that Earth-centered model actually match what they were seeing in the sky, astronomers had to come up with these insanely complex patches. They called them epicycles, literally circles moving on top of other circles. It was a mess. And the argument here is that today's AI is doing the exact same thing. We're just piling on more layers, more parameters, more and more data. These are our digital epicycles, just patches to fix a model that's fundamentally disconnected from reality. All right, so let's dig into the core technical problem. Why exactly are these models so flawed? Well, it really comes down to this. They live inside a self-referential loop. Think of it like a hall of mirrors. All they can ever see are reflections of their own training data over and over again. They never, ever see the actual real world. The fancy technical term for this is topological closure, but here's a simple way to think about it. Imagine an AI living inside a sealed snow globe, and that snow globe is filled with nothing but text. It gets really good at learning the statistical patterns between words, but the mutual information, that's that ICRX approaches zero you see there, between its internal concepts and actual physical reality is basically zero. So yeah, it knows the word Paris shows up next to France and Eiffel Tower a lot, but it has no idea what Paris actually is. It's never seen it. And this diagram just illustrates the problem perfectly. What you're looking at is a pretty advanced AI architecture called GPA, but just look at it. Notice how the whole thing is a closed loop? A prediction only ever gets checked against another internal prediction. There's not a single arrow pointing to or from the outside world. This is exactly why AIs hallucinate. They're not, lying. They're just continuing a pattern that sounds plausible, a pattern that's completely drifted away from a reality it can't even see. And get this, the energy cost to keep this flawed model running, it's just staggering. We're talking about a single complex reasoning task, and some of these models can burn up to 100 kilowatts of power. That's enough to power an entire neighborhood. It's the literal thermodynamic price you pay for forcing a system to check every single piece of information against every other piece just to keep things consistent inside its little bubble. Now, this is where it gets really interesting, because even some of the biggest recent breakthroughs can be kind of misleading. You've probably heard about things like sequential attention, right? It makes models thousands of times faster. Sounds like a huge deal. But the argument here is that this is the ultimate epicycle. I mean, look at the table. It's optimizing for computational efficiency, sure, but it does absolutely nothing to connect the model to reality. So what does it really do? It just lets the AI generate hallucinations much, much faster. Okay, so if the whole problem is a sealed-off bubble, the solution is pretty obvious, right? We have to puncture it. We need a formal mathematical way to connect the AI's internal world to verified real-world measurements. We have to give the system an anchor to reality. So, how do you actually build that anchor? Well, the proposed solution looks to something we all use literally every single day, the internet. Specifically, it's all about the clever way the internet uses two different kinds of addresses to get information where it needs to go. Think about it. To get data to your computer, the network needs your IP address. That's the logical address. It's like the abstract idea of where your device is on the global internet. But to actually deliver that little packet of data, it needs the physical MAC address, which is a unique number hardwired into your actual device. You have to have both, the abstract idea and the physical thing. And there's a protocol that connects the two. And right here, this is the big aha moment. This dual addressing pattern, this idea of a logical blueprint plus a physical expression, it's not just a tech trick. It's a universal principle. You see it in computer networks with IP and MAC addresses, and you see it in biology with DNA as the blueprint and the protein as the actual physical thing it creates. So the big idea is, why not build an AI that follows this same fundamental pattern? Okay, so let's see how this actually works for AI. Instead of IP and MAC addresses, this system uses something called tokens. On one side, you've got the CCI token. Think of this as the logical address. It's the timeless, abstract idea of a Jaguar, locked into a unique code. And then, on the other side, you have the CTI token. This is the physical address, a specific, time-stamped measurement of a real Jaguar at real GPS coordinates at a real point in time. That's the anchor to reality. All right, so we've got our building blocks, one address for the concept and one for the real-world fact. So how does the system actually put them together? Well, it uses them to create a whole new kind of language, a verifiable language made of what are basically semantic Legos. This whole process is called the tokumizer. It takes a simple statement like a jaguar is in a rainforest and splits it into two secure cryptographic pieces. But here's the really cool part. The sticky ends. These two pieces are designed so they can only snap back together if they make sense semantically. So you can't connect a jaguar is in with the concept of blue because the Lego brick for color just doesn't fit into the hole shaped for location. It enforces logic at the most fundamental level, right from the start. So all these semantic Legos get stored in a structure like this one, called an HCNV matrix. Now I know it looks a little complex at first glance, but the real key is what you're not seeing. Unlike the jam-packed, dense matrices in today's AIs, this thing is over 99% empty space. And why is that? Well, because most things in the universe just aren't related to each other. So instead of a slow brute force search through everything, the system just uses that unique token code to jump directly to the information it needs. It's like the difference between wandering through every aisle in a library versus just knowing the exact call number of the book you want. And that massive architectural shift, well, it leads to this, a truly staggering difference in efficiency. We're talking 100,000-fold improvement. When you go from O of n squared complexity down to O of 1, you drop the energy cost from 100,000 watts to a single watt. This isn't magic. It's just what happens when you stop doing all the pointless work. And you're also going from these fuzzy approximate lookups to deterministic, cryptographically secure retrieval. It's a total game changer. And all of this, the efficiency, the verifiability, it unlocks a brand new capability that today's AIs just don't have. It's called active refusal. Here's what that means. If you ask the system a question and it can't find a verified CTI token, a real physical anchor in its database, it doesn't guess. It doesn't make up a plausible sounding lie. It just refuses. It tells you it doesn't have the verified data to answer. For the first time, an AI actually knows what it doesn't know. Okay, so the final part of this argument makes a pretty bold claim. This whole shift isn't just some clever idea someone had. It's an inevitable evolution, and it's being driven by three powerful, completely separate forces that are all pushing AI in the exact same direction. And this really sums up that final argument perfectly. You've got three huge forces at play: thermodynamics, regulation, and biology. Basically, physics, law, and life itself are all converging on the very same conclusion, that real intelligence has to be sparse, it has to be efficient, and it has to be anchored to reality. So let's break those down real quick. First, thermodynamics. I mean, we just can't physically build enough power plants to run a world on these dense, inefficient models. It's not sustainable. Second, you've got regulation. New laws are coming out that demand auditable AI. You have to be able to prove why an AI made a certain decision, and you just can't audit a black box. And finally, there's biology. Nature is the ultimate proof of concept, right? A falcon diving at 200 miles per hour cannot afford to hallucinate. Its survival depends on extreme efficiency and constant real-time verification with the world around it. So here's the bottom line. We're standing at the beginning of a fundamental shift, away from an AI that just strings together plausible, statistically likely sentences. In this new kind of architecture, verified truths, those CTI tokens, they act like they have gravity. They naturally pull other related truths together, forming this coherent, stable structure. And the unverified noise, the lies, they have no gravity. They just dissipate. And that leaves us with one last, pretty provocative thought to chew on. For pretty much all of human history, lies have been cheap and easy to create, while the truth has been difficult and expensive to verify. This technology promises to completely flip that equation on its head. It creates a system where maintaining a lie, an ungrounded statement with no connection to physical reality, is actually computationally and even thermodynamically more expensive than just telling the truth. So the question is, what does our world look like when that happens?